Today's demanding academic research needs sophisticated computing power. What if there was a way to put spare computing power at a university to good use by making it available to others? If we can pool this computing power together, we will be able to speed up research work. That's exactly what the European grid infrastructure does. With the grid, this network of computer servers at universities across Europe supports a wide range of cutting-edge research. Welcome to Stories from the Grid. In this episode, the top quark. The top quark is the heaviest member of the entire family of elementary particles, the tiniest building blocks of the universe, and one of the most interesting. By studying it, scientists hope to find new laws of physics, or maybe even extra dimensions. And grid computing lends a hand to discover where the standard model of physics is not so standard.
The top quark is part of the standard model. So we have a solid theoretical prediction of how many top quarks will be produced in the LHC. However, we don't expect that the standard model is correct. We expect that at these high energies we will see deviations. And these deviations, this will be an indication for new physics. There are many wild theories. Maybe there are more than 3 + 1 dimensions. At very high energies you can somehow enter these dimensions, and that will affect those ratios in the production of top quarks.
Top quarks are created at the Large Hadron Collider, a gigantic scientific device also used to look for the Higgs boson. The LHC is an accelerator where protons and other particles collide at enormous speeds. The resulting crash breaks down the protons into small particles. Every once in a while, the high energy carried by the protons transforms into particles like the large top quark.
The birth of a top quark at the LHC is a very rare process. When the top quark is born, it will decay immediately, so it produces children. Because it has a very high mass, it can decay very easily to the other particles, which are all lighter in the standard model. So from the measurements on its children, we have to imply the existence of the top quark. What we see in the detector are jets of particles. We never see the single quarks which are produced in the initial collision, but we see the final state particles which are produced in jets.
All in all, the LHC produces a massive amount of data. To decide which events should be analysed in detail, scientists take into account only the signals that differ from what is predicted by the standard model of physics.
And to put it simply, we have the data, we have the predicted backgrounds, so we subtract the background from the data and what is left is the signal.
But not all data from the detector can be compared to the simulated data. It's simply too much.
There is an overwhelming amount of background produced also. Every 25 nanoseconds a collision occurs.
Inside the detector, there are kind of firmwares which is built in the detector as a filter. So when a particle flying through the detector, it will trigger some electron signals, and the filter will decide it based on the signal if this event has to be kept. When the data coming out from the detector, they are in the format of the digital signals. You need to go through a data reconstruction process to combine all these digital signals into the information about how the particles are flying through the detectors.
Only after filtering and re-reconstruction of the measured data, we can decide whether we have seen a top quark or just some standard model background. That selection we do on the grid.
So, to wrap it all up, the Large Hadron Collider produces heavy top quarks. By studying how the top quark behaves, physicists hope to find new laws of physics, or maybe even extra dimensions. Because it's unstable, the top quark decays quickly into other particles, so the only way to study it is to look at these children. But the Large Hadron Collider produces an enormous amount of particles, so the interesting events have to be filtered out. The detector does the first round of filtering. The machine only stores data from collisions that give off a specific combination of particles, like muons and electrons. These signals are just digital blips, and they have to be reconstructed into three-dimensional collisions to see what happened. This is done both locally at the LHC and on the grid. After several rounds of reconstruction and filtering, the remaining dataset can finally be processed on a desktop. The results are then compared to a simulated dataset, which tells you what should have happened according to the standard laws of physics. When the real particles behave differently, new physics may be just around the corner. Now we know how the grid has been a great help to top quark research. What more could be possible in the future?
we have to make strong selections already at the detector level and on this local cluster near the detector. When the grid would be more powerful than it is today, it would be unnecessary to do this strong selection. We could process more data on the grid and so enhance our possibilities to discover new physics.
The enormous computing power of the grid has turned out to be an indispensable tool for particle physics. Want to see how the grid is useful in other fields of research? Then join us next time for another episode of Stories from the Grid.